Good evening, everyone. My name is Aditya Sharma, and this is aircraft propulsion course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program. And we are into the second week of this course, aircraft propulsion. And the theme for this week's content is gas turbine and aircraft engines. In the first week's content, we were introduced to we just revised basic thermodynamics, and we were introduced to what are turbo machines. So here discussion is on gas turbines, its various attachments, and different types of aircraft engines. Okay, so we shall start in another few minutes. So let's wait for a few minutes. After that, we can start today's session. Okay, so I believe we can start with the session number pertaining to week number 2 of this course. And the instructor for this course is Professor Vinay Kulkarni from the Department of Mechanical Engineering, IIT Guwahati. I myself am a research scholar here at IIT Guwahati in the Department of Mechanical Engineering. So let's start with today's session. So contents of this session are as follows. So there are two lectures in this week two's content. So lecture 4 is on components of gas turbine power plant and the attachments related to it. And then next is introduction to various aircraft engines and engine performance parameters. So firstly, the performance parameters of a gas turbine engine have been discussed, and after that, various types of aircraft engines have been discussed. Okay, and then there are questions related to each lecture. So first, what we will do for each lecture, we will have first its topics and then its questions. Right. So we have been doing this in previous sessions also. So we will continue to take this session in this session. Okay, so these are the topics of lecture number 4. So first is your gas turbine combustion. So the topics it has are gas turbine combustion, then closed and open cycle gas uh, turbine power plant, then requirement for working fluid in closed cycle plant, right? Then the attachments after that. So multi-spool arrangement is there. Then the steam power plant and gas turbine both when combined, how they work. So we have discussed this in power plant system engineering course also that was being conducted by Professor Niranjan Sahu in the last semester. And then two comparisons have been given. So one is with respect to steam power plant, and then second is with respect to reciprocating engines. So let's see the topics. First of all, so in gas turbine combustion, the essential parts are compressor and turbine. Okay. So its essential components are compressor and turbine. So in compressor, we compress our working fluid, that is air in case of gas turbines, and then this goes to your combustion chamber. Okay, where with fuel combustion takes place, and then this the products of this combustion are expanded in turbine. Okay, so we get the work output from this turbine. And the combustion chamber, in combustion chamber, what type of process is it? It is a constant pressure combustion. So we have seen this in previous week's content, where we have discussed a Brayton cycle. Okay. Then next topic is closed and open cycle gas turbine power plant. So at present, I am discussing the topics of lecture 4 briefly. So closed and open cycle gas turbine power plant. So what do we mean by closed and what do we mean by open? So this has to do with the movement of working fluid in your engine. Okay. If the working fluid that enters the compressor and goes to combustion chamber and from there goes to your turbine, if by some means it is again returning to compressor, okay, in that case we call it as closed cycle gas turbine. And in case it is not returning from turbine, the working fluid is not again coming back to your compressor. In that case, it's an open cycle gas turbine. So the aircraft engines you usually see, right? So turbofan engines you see in your commercial airplanes. So that is an example of open cycle gas turbine power plant. Okay. It is basically like this here. If you have compressor, then here combustion chamber, here. So you see this is compressor and this is turbine. From where it is entering and in that case, this becomes a closed cycle. Okay. So this essentially is the crux of this open and closed cycle. It is visible to you, Prasenjit. If not, you can anytime let me know. Sorry, I got logged out because of network issue. Then the next topic is requirement for working fluid in closed cycle plant, right? So this is very uh, general topic, right? Where what kind of fuel will you have? So this says that you have cheap fuel, ready available fuel. It should be non-explosive, right? It should not be corrosive, or it should not be toxic, right? So all these things have been discussed in this topic. Then is your gas turbine attachments. Okay. So first topic here is multi-stage compression. Then is your gas turbine with heat exchanger. Then is your open cycle gas turbine with external combustion. Then open cycle gas turbine with intercooler and preheater. Right? So in your multi-stage compression, basically means you have in the same engine you have a low pressure compressor and then compressor and then high pressure compressor. Right? Then about your heat exchangers, right? So if we use a heat exchanger in our open cycle gas turbine power plant, so the efficiency increases, right? So that is the purpose of using a heat exchanger in your gas turbine power plant, okay, which is working in an open cycle. Then what is the purpose of your intercooler and your reheater so intercooler basically what does it do? So in compression process, it reduces work input. Okay. So the work input required to compress your working fluid, so it reduces that intercooling with the help of intercooler. Then what does your reheater do? So it increases the power output. So this is basically the purpose of these intercooler and the reheater in an open cycle gas turbine. Right? So open cycle, I hope is clear to you what is an open cycle. Then multi-spool arrangement is there. In a multi-spool spool arrangement, uh, twin shaft arrangement has been discussed, and then twin spool arrangement has been discussed. So twin shaft arrangement, basically you have in the same turbine, you have in the same engine, gas turbine engine, you have two turbines, right? And the purpose of using two turbines is that from the same engine we want variable speeds, right? For our purposes. That is why we are using this twin shaft arrangement. Right? Now, what is twin spool arrangement? Now, what is spool? Spool is basically the arrangement of a compressor and a turbine, right? So, twin spool arrangement, what is this? This basically is we'll have two compressors, right, in line, and then combustion chamber, and then two turbines we'll have in line. So, this basically is your twin spool arrangement. So what is the benefit of using twin spool arrangement? Why are we doing this type of arrangement? So this basically is, this gives better compression, and then for better efficiency also, right? In addition to they can run on different speeds, right? So this is your spool arrangement, right? More than uh, single spool arrangement. Okay. combined gas turbine power plant. So what is combined gas turbine and steam power plant? So this basically is, so you'll have a compressor, okay, we can go simply this way, compressor, then combustion chamber, right, then a turbine. So from here, this will go to your steam generator. So let's say this is your compressor, this is turbine, this is your combustion chamber. Okay. Steam generator, then again here you will have steam turbine. Okay. So Professor Vinayak also has shown some gear arrangement here also, right? So that is also one aspect of it. But basically the output from the output of working fluid from the turbine. Okay, so this has energy left in it. This energy can be used to generate turbine. So this basically such an arrangement or such a combination is your combined gas turbine and steam power plant. Basically, the heat from the exhaust of your turbine of this gas turbine power plant is being used to have the steam for your steam power plant. Then is comparison between steam power plant and comparison between steam power plant and gas turbine, and then between steam power plant and sorry gas turbine and your reciprocating engines. So comparisons, if you see, steam power plant and your gas turbine power plant. What is the comparison? So basic differences of the working fluid, right? Here water is used, here gas is used. Okay. So here phase change takes place. Here there is only single phase. Right? This works on Rankine cycle. This works on Brayton cycle. Right? So differences, comparisons like these have been drawn. Then for your reciprocating engine and your gas turbine power plant. So this has higher weight per kilowatt. Okay, the power that is this engine is generating. So with respect to that, its weight is high. For the gas turbines, the advantage is this is low. Okay. Then comparison of efficiencies have been given. So its overall efficiency is high. So what is overall efficiency? That also we shall discuss. So comparisons like these have been given under this topic. Okay. Now after that, these are the topics of lecture 4. Okay, where combustion, open cycle, closed cycle, working fluid, gas turbine attachments, spool arrangements, multi-spool arrangements, and comparison with other power plants. Then move on to questions. So first is this question. Please try to answer this. So any answer from your side? Path, Prasenjit, if you are there. Okay. So path is saying used in aircrafts. So the question asks that find the incorrect statement for an open cycle gas turbine. Prasanjit is saying B option. So if you see your first option, it can have sorry, only air as working fluid. This is correct, right? So it allows only internal combustion, right? And all types of fuels can be used. So it is used in aircraft applications. So D is correct, A is correct, right? But if you go back, right? So we have a special case for your open cycle gas turbine with external combustion also. So in that case, also if you see this C option, all types of fuels can be used. So if you see your discussion in the lecture 4, you will see that for your closed cycle gas turbine power plant, all types of fuels can be used, but I believe this is not for the open cycle gas turbine power plants. Okay, in that case, I believe second B and C options will be correct. All right. So though I have given B also, but I believe it will be B and C. Right. So this is your question number one. Right? It's C option. I have to again check. So I'll see that. So moving on to next question. This is on your Brayton cycle. Please try to answer this. So I have got constant pressure as the answer. So we have seen in previous week's content. I'll just again draw the PV diagram of Brayton cycle so that we can again revise this. So it is something like this, right? From here to here, here to here, here to here, here to here. This is, I believe, heat addition. This is heat rejection, right? So this is constant pressure process. This is also constant pressure process. This is constant. This is constant entropy process. This is also constant entropy process. Okay. So in Brayton cycle, heat rejection takes place at constant pressure, constant volume, first at constant volume, then at constant pressure, first at constant pressure, then at constant volume. So here, option A is correct. Okay. The Ts of temperature with respect to entropy. So how is this diagram? This basically is like this. Just to revise, it is like this. Okay, so this is 1, 2, 3, 4. It is 1, 2, 3, 4. So this is your Brayton cycle from previous week. I hope this is clear. Then moving on to next question. Please try to answer this. So this question number 3 says that a single shaft arrangement in a gas turbine engine is more suitable for dash speed and dash load applications. So twin shaft has been discussed. Yes. So we have discussed why twin shaft is used. Twin shaft arrangement is used. Now here question says the single shaft arrangement, why we use it. So we have four options. First is your fixed, variable, variable, fixed, 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 variable, variable. So we have seen in the twin shaft discussion that the twin shaft arrangement, we have two turbines, right? With each turbine having different speeds for different application applications. So opposite to that, your single shaft arrangement will have fixed speed and fixed load applications. Okay. So in that case, C option will be correct, right? Then after that, next question. So this is a numerical type of question. So please read, have a look at this question first. After that, we shall solve it. Assignments, or in this week's assignment, the numericals are not that lengthy. So question number 4 says that for a Brayton cycle with the compressor inlet temperature and the cycle pressure ratio are 298 and Kelvin and 6 respectively. The turbine inlet temperature is. Okay. So how did Prasenjit got his answer? What did he use to solve this? On your mic and explain if you wish to, if you're comfortable. So first see that question number 4. So first we have the Brayton cycle. Yes, one, two, three, four. 1 to 2 is your compressor. This is your combustion chamber. This is your turbine. Okay. So now we have been given P1 is 298 Kelvin, right? And the cycle pressure ratio is given as 6. Given as 6. Now for maximum work output, we have for maximum work output, we have Rp raised for gamma minus 1 by gamma equals to T3 by T1. So this is maximum work output. Now let's place values. Now if you solve this, you will get let's calculate this. So this comes out to be 829.6 Kelvin. Okay. So this basically is the answer to this question. And this is about lecture number 4. Now, in your lecture number 5, let's see the topics that you have. Engine performance parameters and the introduction to various aircraft engines. So first, we will see the performance parameters. So all these we shall see one by one. Lecture 5, first of all, let's draw the an engine. Okay. This is your intake. This is subscript A is for air. This is pressure from outside. And this is exit velocity of jet, right? And this is basically your area at the exit and pressure at the exit. Now, if you have to define thrust, the first parameter here is thrust. Thrust here is composed of two components. First is your change in momentum of your working fluid, right? And then is the pressure difference between your inlet and outlet, right? Your front and back. So your change in momentum. So if you talk about thrust, so this is mass flow rate of So this. So this is your thrust. All right. Then what is your thrust power? When you multiply force with velocity, that gives you power. Right? So this basically is mass flow rate of air, right, dot Ca. If this component we don't write here, in that case, this is your thrust power. Now is your propulsive efficiency. So this is denoted by this eta, I believe it's called eta subscript p. So what is propulsive efficiency? This basically is thrust power divided by change in kinetic energy. So change in kinetic energy of what? Change in kinetic energy of your working fluid. Okay. So the energy that has changed in your working fluid by virtue of your combustion. From that, what energy will be, what energy will come out as your thrust. Okay, that basically is your propulsive efficiency. I hope this is understood. So this is your propulsive efficiency. Okay. So let's take 5 minutes break because it has already been more than an hour since we have started this session. So let's take a short 5 minutes break. After that we shall continue the session. Okay, so let's continue with the session. Then we have seen propulsive efficiency. After that, we have energy conversion efficiency. Now, what is this? Now, some part of your energy that you are giving from your combustion is converted into your change in kinetic energy of working fluid. Okay, so the heat released from your fuel, right? Not all the heat released from fuel is goes into conversion into increase in the kinetic energy of the working fluid. Okay, so this is denoted by this. The amount of energy that goes as change in kinetic energy of working fluid. It is to the input fuel energy. Okay, so this is this. So this is your energy conversion efficiency. Then is your overall efficiency, which is thrust power by input fuel energy. So the energy that we take from fuel and the energy that we get in form of thrust. So this can be obtained from here. So if you see this and this, you'll find out that when they multiplied, they give this only. Thrust power divided by input fuel energy. Okay. Then your thermal efficiency is there that we know, right? That is common. After that is specific fuel consumption, SFC. What is SFC? SFC basically is mass flow rate of fuel divided by thrust. All right. So this is your specific fuel consumption. Then after that, redefining thrust and takeoff thrust. These two also have been discussed. So this I'll skip here. You can check it in the lecture number 5. Then aircraft range has been derived. So this derivation also you'll have to see in lecture number 5. So I'll provide the link of lecture in the description. All right, of the video that I'll be uploading on YouTube of this session, this recording only, basically. Right. Okay. So this is about your parameters. Now after this, there are different types of engines have been introduced to us. So first is your piston prop engine, right? So here, what is this? We have one propeller, and then this is somehow connected to your piston engine. Okay, so this is piston prop. Turboprop is you will have a propeller, but here you'll have some turbine arrangement. Okay, by means of that, this your propeller will run. Okay, so this is basically your turboprop. What happens in turbofan? So in turbofan, uh, the arrangement is such that in front of this engine you'll have one fan. Okay, so aircraft engines. So at the front of this, the commercial aircrafts you see, right? In those commercial aircrafts, mostly you'll find turbo fan engines. Okay, so in front you have some fan fan arrangement. So this is your some fan arrangement for the inlet of your air or working fluid. Then what happens is your engine is here, right? Here you have compressor, then combustion chamber, then turbine, and if there is nozzle also. Some air is bypassed. All right. So this is your main engine, okay, and some of your working fluid is bypassed. This doesn't go or follows the Brayton cycle. This basically is your turbofan engine. All right. Turbofan. Then in turbojet, if you remove the this fan and all arrangement, right? In that case, this becomes just turbojet. Okay. So at high max, this turbojet is used. Right? Then ramjet also. So in ramjet, you don't have any specific compressor for compression as such. Okay. So, and this also works for very high Mach numbers. Then there is comparison between your different engines based on at what altitudes they work and what Mach ranges they work, right? So if you see your turboprops, they work below zero point 0.5 Mach, right? And at altitudes around 6,000, right? It's around 6,000 meters. Then turbofan works around 10,000 meters up to, and Mach ranges between zero point 0.5 to 1 for turbofans. And for turbojets, you have high Mach range. So as per lecture 5, this is from 2.5 to 3. This comes in this range. And the altitudes at which this can work is also pretty high. So this is in this range of 20,000 meters. Right? This is comparison between these three types of engines. Then based on your propulsive efficiency and the speed of your aircraft or inlet speed. So this is something like this. Something like this. So for your same uh, inlet velocity of your working fluid, the propulsive efficiency for high bypass turbofan will be higher. Then comes your low bypass turbo fan. Then your turbojet comes, right? And for your turboprop, what happens is up to certain point, this efficiency, propulsive efficiency increases. After that, it starts decreasing as the velocity of the aircraft increases further. All right, so this is about your aircraft engines. Now moving on to questions based on lecture number 5. So first question we have. So please read this question and try to answer this. This is a straightforward question. Energy conversion efficiency of the aircraft is defined as the ratio of. What is energy conversion efficiency? So in energy conversion efficiency, you have kinetic energy, change in kinetic energy involved, and then fuel energy is involved. Okay. So from the given options, option C comes out to be correct one. All right. I hope there is no doubt in it. So moving on to next question, question number 6. A jet engine has higher efficiency at. So we have four options here. Option So moving on to next question. So we have question number 6 here, which says that a jet engine has higher efficiency at dash. So we have four options here. First option is high speeds. Second option is low speeds. Third is high altitudes. Fourth is low altitudes. So what happens is two things here play a role. First is you have to understand that as we go higher in altitude, the air becomes thinner, right? So the air becomes thinner. This reduces the basically thrust, right? But if you go higher, right, the thermal efficiency increases. All right. Yes. So as the air becomes thinner, the thrust reduces. But with your increase in altitude, your thermal efficiency of the engine also increases. So these two, there's a tug of war between these two. So whichever uh, uh, whichever factor weighs higher wins the race in deciding uh, whether the efficiency will be higher or not, or on which factor the efficiency will depend. So at higher altitudes for jet engines, as we increase the altitude, your efficiency increase. But this is to some level, all right, for jet engines. So your thermal efficiency factor weighs higher in comparison to your thinner air factor. So this is your question number 6. And answer to this question is C. Right? So this is question number six. So correct option is C. And next question. Let's see next question. Please read this question and try to answer this. So air pressurized in ramjet engine is accomplished by The question is about your piston prop engine, right? The propeller being driven by a piston engine. So four options have been given: at high speed and low altitude, low thrust and low altitude, low speed and high altitude, high thrust and high altitude. So piston prop, if you see this, so these diagrams are based on, these questions are based on this diagram. So this is your turbo, turbo prop. This is what turbo. So this says that piston prop engine is more appropriate for four options we have. So out of this, the piston props are used for your first low altitudes, right? And then for low thrust. Okay. So B is the correct answer to this question. Then move on to next question. So this is about propulsive efficiency of aircraft engine. Please read the following options and try to answer this. Yes, C is the correct option. So it is equal to 1 when the air intake is equal to jet velocity. Because your propulsive efficiency is also written as 2 by 1 plus Cj by Ca. So if Cj and C are equal, then this becomes 1 plus 1. And in this case, this becomes 1. So this is correct. is the correct option. So this question is about turboprop engine. We have to find out incorrect statement. This is very plain question. The turboprop we know doesn't go for supersonic speeds. Okay, so clearly B is the one. All right. Then we have last question of the session. So an aircraft engine has incoming air at velocity 250 meter per second and exhaust at 620. The propulsive efficiency of the aircraft is. So question number 11, solution. Propulsive efficiency I just told you is 2 into 1 plus Cj by Ca. That is 2Ca by Ca plus Cj. So if you place the values, it comes out to be 0.57. Alright. So this is it about session. So I'll conclude this session in that case. So there were two lectures in this week's content, lecture 4 and lecture 5. Lecture 4 was on your aircraft, your combustion, right? Gas turbine combustion. Then open cycle and closed cycle in gas turbine power plants were discussed. Then fuel to be used for closed cycle power plant. This was discussed. After that, attachments were discussed. What is the twin shaft arrangement and twin spool arrangement and multi spool arrangement? So these were discussed in your lecture 4. And at the end, comparisons were drawn with respect to your reciprocating engines and your steam power plants. Right? So gas turbines were compared with these two. So we saw questions on this. After that, uh, there was lecture 5 where engine performance parameters were introduced to us. Parameters like propulsive efficiency, overall efficiency, energy conversion efficiency. Yes. So what is thrust power? What is thrust? What is specific fuel consumption? So all these were discussed in your this lecture 5. And after that, uh, an expression for the range of aircraft was derived, and then basic introduction was given of different types of aircraft engines like piston prop, turbofan, turbojet, ramjet. So all these were discussed in this week's content. So then we saw the questions based on lecture number 5. Right. So this will be conducted our session number 2. All right. Thank you. Thank you for joining this session. Next session again will be on next Tuesday. The timing will remain same from 6 to 8 p.m. Till then, bye.